Okay, so we're going to be talking about chapter one. We'll get through a good chunk of the chapter, potentially all of it, but we will see. Okay, so let's go ahead and okay, and there we go. Okay, so can everyone see the slides okay?
Yes.
Okay,
Yes.
and my audio
Yes.
is good?
Yes.
Yes.
Thank you. I appreciate the confirmation. Okay, so chapter one, Introduction to Astronomy. Very general chapter, no particular topic. Uh, every subsequent chapter will always be, one particular thing: terrestrial planets, stardust, galaxies, whatever. But not this one. Even chapter two, which is, kind of about the history of astronomy and looking at the night sky. So we're going to start talking about grapefruit. The natural start to any astronomy class is this citrus, loved by some, hated by others. So we're going to imagine that the sun is a grapefruit. We've just chosen the grapefruit because it's the correct shape, being a sphere, and it's a relatable size. All right, and a convenient size for the analogies we're going to make. So if the sun was the size of a grapefruit, then the Earth would be the size of a ballpoint pen. Okay, which is quite, it's the ball at the tip of a ballpoint pen. So quite a bit smaller. As this image shows, the Earth is like a tiny drop compared to the sun. The sun is 99% of the mass in the solar system. That means all the planets, including even the big ones like Jupiter and Saturn, make up only 1% of the total mass of the solar system. Because not only is the sun much larger, it has a very dense core. And, if the Earth was to fall into the sun, it would just, hardly cause any damage at all. Now, at that same scale, let's consider distances. Let's consider Earth's orbit around the sun. Well, if you put the sun at the 0 yard mark on a football field, the Earth would go at the 10-yard line. So that's about 30 feet. So we have, exactly 30 feet, right? If it was 10 meters, it'd be about 30 feet. But if it's, 10 yards. So think about that distance. Ballpoint pen, grapefruit, nothing in between except for two other planets, Mercury and Venus, but mostly just empty space. So it really gives you an idea of the vastness, the vast emptiness of space, even within our own solar system, even within the inner orbits of the terrestrial planets, the rocky planets like Earth. If we were to consider the whole solar system, at least out to the orbit of Pluto, a dwarf planet, former planet, now classified as a dwarf planet, but well known, well loved. Well, Pluto's kind of, the edge, right? It's not the true edge. There's actually quite a few things past Pluto, but they're not as well explored or as well known. So it's a good kind of demarcation. And if we think of the distance from the sun to Pluto, that would be 4 football fields. So at that scale, right? Think about how many ballpoint pens it would take to line up to cover a distance of 4 football fields. Well, that shows how small Earth is compared to the overall solar system. That's why when we send a space probe, even at thousands of kilometers per second, so really great velocities, which we can achieve in space because there's no drag, right? No air. Well, even then, it takes years to send these types of space probes out to the edge of the solar system. The mission that went by Pluto and captured the image that we see in this figure, it took 8 years to get there. So, gives you an idea that it's a vast, vast distance. But those distances are nothing, and those distances being the distances within our own solar system, are nothing compared to the distances between stars. The nearest star to the sun, which is our local star, right, is Alpha Centauri. And Alpha Centauri is 4.36 light years away. Okay, well, that's a lot of kilometers. We'll talk about the conversion, all right, as we go along. But at the scale of the grapefruit, it would be 2,825 miles, or all the way across the continental United States, all the way from San Francisco to Washington, D.C. So all the planets, right? Even out to Pluto, which is this distant, remote planet in our solar system, all of that is like the size of a park, right? 4 football fields. Well, that park is on one side of the country, and another solar system with its own planets and, another park-sized solar system would be all the way across the country. And in between is what? Basically nothing, just empty space. And if it takes us 8 years just to get to Pluto, which is the edge of the park, how long would it take to get all the way across the United States? You know, it'd be like asking a snail to travel from San Francisco to Washington. Okay. So, do you think that it's possible to travel to another star? What do people think? Anyone have a speculation? Could we travel such a great distance?
Potentially, maybe with a strong enough rocket, maybe.
Yeah, that I exactly, right? We would need very different rockets than the one that took 8 years to get to Pluto. Yeah, so we have to really design some much, much faster rockets that are fundamentally different than the ones we have now. Yeah. Yep. Now we're going to cover a little bit of math with the exciting title, Numbers and Units in Astronomy. It's good to get this out of the way. And the stuff we're going to talk about is some of the most salient and frequently seen concepts that you'll see throughout the numerical or math part of the class. First of all, and this part I think is kind of interesting, is thinking about how all the physical sciences, and this is true of basically any calculation that you're making that involves numerical calculations. It is based off of a unit system called the Système International, or SI for short, which is synonymous with the metric system. So those terms can be used interchangeably. And everything from energy to momentum to talking about intensity and power output, all those types of concepts, even force and acceleration, velocity, they're all built on these base units. So all those other terms I just mentioned would have unit expressions that are called derived units. And those derived units would be like words formed out of an alphabet. And the alphabet in this case has 7 letters, which are C, D, M, O, L, K, A, S, M, and K, G, where each of those is like an individual letter, so to speak. And some of these we don't care about for astronomy, at least not in this particular class. Candela is a way of measuring brightness, which would be relevant to astronomy, but we're not going to cover it. Moles, which is what MOL stands for, are used in chemistry mostly. We will talk about temperature. Temperature is represented by the unit uppercase K, which stands for Kelvin, which is the temperature system that's used in the sciences instead of Fahrenheit or Celsius. Uh, a stands for amperes, which is the unit for the current and the base unit for all of electricity and magnetism. And although magnetic fields are important in astronomy and we'll discuss them qualitatively, we won't be doing any calculations with them. So besides temperature, we're going to be working with S, which is seconds, the units of time, M, which are meters, the units of length, and kilograms, which, kg, which are kilograms, the unit of mass. So those are our building blocks, our letters that form our alphabet, and we can derive everything from them. There's nothing else. There's no other hidden unit, hidden quantity. Everything is formed by these concepts, which is a powerful statement if you think about it. So mass, well, the kilogram is the standard international unit of mass. Do notice that it's the kilogram, not the gram. That's an easy mistake to make. Just keep that in mind. So 1 kilogram is equal to the mass of about 4 apples. Okay? Now, that's only true on Earth. If you took, like, well, I guess I should say, like, saying that the so the mass is always the same, right? So if you took apples to the moon, they would have the same mass of kilograms, but to show them on a scale is a complicated idea because if you took the scale to the moon, it wouldn't read the same amount because scales actually read force, which is weight. Weight is a force, and that's not mass. But we often kind of conflate the two. We, take the two and just say they're the same thing because most of our mass measurements are made on Earth. But of course, in an astronomy class, we want to consider, weighing things on other planets where the mass stays the same, but the weight would not. And if you wonder what I'm talking about, just think about how, when you see videos of people on the moon, they seem to be much lighter. They can jump further and so on. And that's because although they have the same mass, they have a different weight because there's less gravity on the moon. Okay, so using that basic unit of the kilogram, let's talk about the mass of the Earth. And this is going to be a segue because notice the mass of the Earth. It's 5,972,000,000,000,000,000,000,000,000,000,000,000, which is totally unintelligible if you were to say it out loud like I just did, right? It's too many repeated zeros. Even when you read it, it's hard to really make sense of that number. And that's why in astronomy, we very often use scientific notation. So we will often express numbers like masses of planets and stars in scientific notation. We'll do that with distances as well. We'll express a lot of distances in scientific notation. So this full number with all of its zeros gets expressed as 5.972 times 10 to the 24 kilograms. Okay? So that's the way that we write scientific notation. The value in the front, the 5.972, is called the coefficient. It can have as many significant digits as it naturally has, okay? And we'll talk about more about significant digits later. In this case, it has 4. But what's important is that it's between 1 and 10. That's always true. The coefficient is always between 1 and 10 when you write scientific notation. For example, you could not write 59.72 times 10 to the 23 because even though that would be numerically equivalent, it would be the incorrect form. Okay? Hopefully that makes sense. It's might sound a little bit of a picky aspect, and it's not going to make or break getting the correct answer. But if you're not sticking to the correct form, you're going to end up confusing yourself, potentially. Okay, so just to clarify a couple of things about scientific notation. And before I do, who's seen scientific notation before? Anyone?
Me.
I have, but it's
Okay.
been a
I haven't.
lot of
Yeah,
years.
I've seen it before.
All right. Yeah. So I expected a few people to see it before, and yeah, have a vague memory of it. Yeah. And some of you haven't. Some of you might as well have not. And it will just take a little bit of a refresher. If the concepts that I just mentioned now don't quite land, there's just a quick Google search. There's so many good videos that will come up. Just like a 4-minute video, just like summarize it for you. That can be good if you just can't quite remember how it works. So numbers, and you obviously will have my homework tips right as well to see how I've done it. The numbers in scientific notation have a coefficient between 1 and 10. Okay, coefficient, notice the blue there, multiplied by a power of 10. That's what we saw with Earth, right? The power of 10 was 24, and the coefficient was 5.972. All right. And the 24 represented how many places you moved the decimal. So, they show the arrows, 3 of them. Well, if they showed all of them, it would keep going and there'd be 24 until the decimal finally landed between the 5 and the 9. All right. So 4.2 times 10 to the 9, the coefficient is 4.2. The power of 10 is 9. Okay. We also sometimes refer to the power of 10 as the order of magnitude. Those are the same, they have the same meaning. Order of magnitude, it can sound a little confusing, like what do we mean? I'm in the habit of using it. I've been using it for so many years now. I'm used to saying, oh, it's 3 orders of magnitude bigger. Well, 3 orders of magnitude bigger means 1,000 times bigger, right? So it's kind of a strange way of saying that. But when you're thinking about powers of 10, it does become natural to just refer to them as orders of magnitude or just powers of 10. So the order of magnitude in the case of the example number is 10 to the 9, which you could describe as 1 billion. It's fine to use terms like a million, a billion, a trillion. It's just that they don't really go beyond that, not common terms. So anything bigger than 10 to the 12, which is a trillion, doesn't have a common name for it. So that's, there's a limitation there. Okay, so why use scientific notation? Because the distances, in this case described as sizes, between objects or just the size of things, like here we have the distance to Andromeda, that these values are so big that it wouldn't make sense to express them any other way. Okay? Now, when we use light years, which are also a measure of distance, we can kind of get away with not using scientific notation because a light year is so long. A light year is about 10 trillion kilometers. So it's already a huge number. So it's actually kind of convenient as a unit for describing, stellar distances or galactic distances. By the way, when I mentioned Andromeda, does anyone know what Andromeda is? What type of celestial object? What type of object is Andromeda? Well, I guess nobody knows. Okay. Well, I will keep it as a mystery for now, but we'll know in a few minutes. Okay, so let's talk about conversions from from normal numbers to scientific notation. A lot of this will repeat what I said a minute ago, so I'll go through it quickly. When converting to scientific notation, you count how many digits you move the decimal to achieve a whole number coefficient. So you're moving that decimal from a point where it's after all the zeros and it's basically on the far right, and you're moving it to the left. Okay? So if you move to the left, then you're multiplying by powers of 10 so that you're getting a positive value in the power. Now, sometimes you move the other way. When you have a really small number, which doesn't happen that much in astronomy, but sometimes we do have some constants that are small, then you have to move to the right. Okay? So in that case, you subtract by a power of 10. Let's look at 2 examples. All right, so 25,000 expressed without scientific notation can get converted to 2.5. Notice the coefficient is between 1 and 10, coefficient being 2.5, times 10 to the 4. Okay? So there we have a positive power because of the direction we move the decimal place. When we move it to the right for a small value like 0.0384, we end up with the scientific notation expression of 3.84 times 10 to the negative 2 because we divided. All right? So negative exponents or negative powers of 10 represent division. Positive powers of 10 represent multiplication. Now, how do we do arithmetic with scientific notation? Well, this is actually one of the most common mistakes I see on students' work, is that they make a mistake with this step. So with that in mind, pay attention, because you want to avoid that mistake if you can. When we multiply, the coefficients multiply and the powers add. So this is because of something called the law of exponents, which you might remember from a math class. It's fine if you don't. So if we take two scientific notation expressions, 2 times 10 to the 3 and 3 times 10 to the 2, well, when we multiply those together, the 2 and the 3 just multiply normally. They get the 6. But when we multiply the 10 to the 3 and the 10 to the 2, the effective way to do that is to just add the exponents. So add the powers, 3 plus 2. So we end up with an answer of 6 times 10 to the 5. All right. If we were to write out the full numbers and just do, like the whole multiplication, you would see why this works. All right. But it's just a shortcut to remember that you just add the powers. If you divide, well, then you subtract the powers. Okay. So you divide two scientific notation expressions. You do normal division for the coefficients, just like with any old number. And then with the powers of 10, you subtract. So for example, 4 times 10 to the 3 divided by 2 times 10 to the 8 becomes 4 divided by 2, which gives us the final coefficient of 2, and then a power of 10 raised to the 3 minus 8, or 10 to the negative 5. So our answer is less than 1. Okay? Any questions on that?
Is all this math supposed to be done just in our brain, or are we going to be able to use a calculator for these equations?
Yeah. So using a calculator is a great idea. I highly recommend it. It's more like it's good to know how it works so you can see, like, that way you could catch a mistake if you made a mistake in the entry into the calculator. So it's like you kind of, you know what I mean? Like, you don't want to rely on the calculator blindly, in a sense. That's all. And the only reason that calculators can get it wrong is because people forget to put in parentheses.
Yeah, so the equation I just have to learn how to do the equation to be able to use the calculator effectively.
Yeah. Yeah. So yeah, it is. Yeah, absolutely. Yeah. Yes. Yeah. Since you never have to do it by hand. You can always use a calculator, as long as you feel confident that you always you know where to put parentheses, like the ones here. Then yes, then you could absolutely ignore this rule and just always calculate it. Yep, that is right. Yeah, and then as far as like a really good calculator, it's Desmos is excellent to use, um, because you can write everything and it looks like you would, like it's typed, rather than as on like a scientific calculator where it's all one line. So I highly recommend using Desmos or something similar for doing your calculations. All right, so we're not doing this exercise. Okay, so that's enough of our little math primer right now. I now want to talk about the scientific method. Sure, you've heard of it before, right? We hear about it from grammar school on. And the context, I guess, I want us to think about it is that this scientific method would be a good way to define the difference between astronomy and astrology. So astrology, it's got, like this whole system of what planet you're born under, depending on, like, the Earth's position when you were born, as well as, the constellations that don't change that much, but the planets do change, right? So there's this whole thing that you're associated with a planet, but also a constellation. And so, so then someone born in the same month would always have the same constellation, but if they're 10 years apart, they might be associated with a different planet. And that's kind of cool. And it's all about, just tracking the planets, right? But there's nothing scientific about it in that it doesn't follow the scientific method. There's no testable hypothesis. There's no experiment. There's just a set of rules that give you the same outcome. And so it's like the rules of a game or something, or like I said, a belief system. And it's gratifying and interesting, but there is nothing testable about it. I guess, people say that it's associated with certain traits and so on. And I guess you could say, oh, well, you could test if that's true. But when studies they have always shown that there is no, correlation between particular personalities and, astrological signs. So, although it has been subjected to the scientific method, you could say it hasn't passed. Not a condemnation of it. That's just not scientific. That's all. Okay. So anyway, scientific method. You have observations. That's kind of where you start, right? You're interested about something. You have a sense of inquiry, of questioning the world around you, and those observations lead to questions, right? Or maybe even you start with a question, right? So these come together because you may just have a question, or you may have an observation that leads to a question. Now, then that question gets formalized as a hypothesis. The difference between just a question and a hypothesis is that the hypothesis is a testable statement. So saying, you know, why do birds fly is not a hypothesis, but it is a question. Saying that birds, you know, like it birds fly because they generate lift with the flapping motion and the variable densities of air would be a testable statement, right? Because you go, okay, we're going to see if flapping matters. We're going to measure densities with some sort of probe of some sort, some technique, right? So that's the idea. The hypothesis has to be testable. It's reformulating the question. That leads to predictions because you say, okay, well, if we get this result, then that means that our hypothesis was correct. If we get a different result, then we have to reject our hypothesis and come up with a new one. Okay, so that's kind of the role of predictions. Of course, then that leads to experiments. That's where you test your predictions, the predictions that came from the hypothesis, that came from the questions and observations. If you don't get the results you expected at all, and maybe you didn't disprove your hypothesis or prove it, then or support it or not support it, then you might just have to go back to basic observations, right? So it can all start over. But it can also kind of come up with some definitive results as well. All right. So that is the scientific method in short. Now let's get back to the scale of the universe, kind of like we were talking about when we were talking about the grapefruit, but without the fruit. Okay, so we're just going to work our way down. The universe as a whole has a size of 8 times 10 to the 26 meters. So, I mean, that number is hard to make sense of until we see it compared to other ones. If you remember the table from a few slides back, then you could do that comparison, but we'll make it as we go along. Do note that distance is equivalent to 93 billion light years. Okay, so 93 billion light years or 9.3, right? In terms of, 93 billion, I guess is the best way to say it. Okay, so here is the entire universe shown in one representation. This kind of way of showing it is looking at something called the cosmic microwave background radiation, which is a leftover signal from the Big Bang. And because that signal is everywhere, it's a kind of natural or intuitive way of showing the universe as a map. Other ways of mapping the universe would be with galaxies and all the galaxies that we've located. All right, so we've done these huge surveys of locating galaxies and creating these big, kind of like even 3D maps to show the most of the known or observable universe. Obviously, that's an incredibly daunting task, and it's something that's ongoing. But here would be the entire diameter of this spherical universe, and thinking about what it means for the universe to be a sphere. Is there an edge to the universe? Those are questions that we will save for another day. They do have answers in terms of the current theories based off our understanding of cosmology, which is, I know I'd mentioned that we talked about it much later, but I'll just kind of quickly define it. Cosmology is actually the study of the cosmos as a whole. So it's the science that approaches questions like, where did the universe come from? Does it have an edge? What what was the Big Bang, things like that. Okay. So the next largest kind of scale in the universe are these things called voids. And voids are very strange. We don't cover them too much. They're an absence of matter. And what they are these huge gaps between galaxies. So this sort of cone-shaped figure represents a scan of the universe from one point. So you could think of, Earth as being the very bottom of the cone here, and we're looking out almost like radar, and we're scanning, out to some great distance and looking at all the galaxies we can locate. And as we do that, we're, of course, looking back into time. So the galaxies that we're seeing at the very edge of our scan are so-called primordial galaxies that don't exist anymore, as far as we know, right? And our theories suggest that they haven't, that they would have evolved into other types of galaxies, because we're looking back tens of, over 10 billion years into the history of the universe. And that has to do with the limitation of the speed of light. But more importantly, and relevant to voids, if we look at kind of the way that galaxies are clustered, especially in the more contemporary universe, as where I'm moving my cursor right now, we can see that they cluster into kind of long strings or tendrils, also called filaments, and into clumps as well. And so what I'm referring to here are all these dots of either green or orange color. What the colors represent is actually density, because in this figure, the galaxies themselves would be too small to show. They'd be less than a pixel in size. And so when many of them are together, we'd represent a cluster of galaxies as an orange region. And where there's just a few galaxies, it would be green. And where there's no galaxies, then it would be black. Well, where there's no galaxies are the voids. So the void edges are dense with galaxies, but the voids themselves are mostly absent and have ultimately at their center nothing. Did you have a question? All right. So the reason there are voids has to do with how the universe was created in the Big Bang, and the fact that gravity has been pulling galaxies together ever since. It is something that we'll come back to. Very interesting idea. All right. But they're huge. And if we look at that size, 1.5 times 10 to the 24 meters, the best way to consider it is compare it to the size of the universe as a whole. Because although they have different coefficients, 8 and 1.5, if we look at the powers of 10, they're 2 apart. So if the universe has a power of 10 to the 26 and a void has a power of 10 to the 24, what is the difference in the size? How would you describe the difference in the size? How many times bigger is the universe compared to an average void? Anybody?
We're looking at the size on the chart, right?
Yes, yes.
Okay. 7.5.
So the universe is 7.5 times bigger than a void?
Yeah. Just
No,
on the chart, or
not quite. Because if you plug that in your calculator, if you took 8 times 10 to the 26 and you put parentheses around it and then you divide it by 1.5 times 10 to the 24, you will not get 7.5.
oh, my bad, my bad.
So just actually ignore the coefficient right now. Ignore the 8 and the 1.5. What would you get if you just compared the 10 to the 26 and the 10 to the 24? How many 10 to the 24s would fit in a 10 to the 26?
Just two.
No, that's the power differences too. But when we say about multiplication, it's not two. What does it mean for something to be 2 powers of 10 bigger? How many times bigger is it? And you don't have to answer again if you feel like you're being put on the spot. Maybe someone else can jump in. How much?
100.
Yes, 100. So 2 powers of 10 is a difference of 100. Very good. Yep. 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 And that's not an easy idea. That is the core of scientific notation. And like I'm familiar with it. It seems easy to me, but I'm doing it for years. I get that it can be strange. But if you can like have that handy as a quick idea that can make sense to you, you'll be in such good shape for a lot of the math that we do. All right, so we got a few more scales that I'll talk about and then quickly get to another question. All right, so we have the Virgo supercluster local group. These are clusters of galaxies. So here's the Virgo supercluster, which is like thousands of galaxies. Actually, it's tens of thousands of galaxies that are in one huge cluster, one of those clumps. And it's cool because it actually creates such a big gravitational effect that it bends the light waves. And so looking at the size of the cluster, it's about 1 times 10 to the 24 meters across. All right. And the cluster they're showing is actually, to be honest, cluster Abel, because it's this is such a good one for pictures. But it's similar in size to the Virgo supercluster. Okay. And so we can see that really they're like comparable in size. So the biggest clusters are comparable to voids, but many groups of galaxies, like the one that our own Milky Way galaxy is in, are about 10 times smaller. See, 10 to the 23 for the local group. That's the name of the galaxies that includes our Milky Way, right? So that would be kind of like the size of something that's 10 times smaller, right? Although, to be honest, this little blue thing here looks like it's more like 5 times smaller, right? But approximately 10. Okay, so then our local group is made up of 3 spiral galaxies and a bunch of smaller dwarf galaxies. And there's also 2 elliptical galaxies that are in our local group as well. Okay, so this is getting into types of galaxies, which in this chapter is really just touched upon. We have whole chapters down the line where we get into classifying galaxies. So, like a lot of things we do in chapter 1, we did kind of like introduce the terms, but they're not really formalized as much yet. All right, and there's all the dwarf galaxies I mentioned, 50 plus. Okay, so all these galaxies are just clusters of stars, but we don't call them clusters because they're so big, and their mechanics, the way that the way the spiral galaxies rotate, the way the elliptical galaxies have evolved, are really distinct to things on this scale. They even relate to dark matter in a really important way. Although dark matter is a as yet not fully understood phenomenon in astronomy. But anyway, it's always easy to jump ahead with these overview stuff. Is that when we talk about galaxies, we're talking about billions of stars. So the Milky Way galaxy, okay, which obviously this is not the Milky Way galaxy, although we think the Milky Way galaxy looks something like this. And we know it's not because we can't fly out of the Milky Way galaxy and observe it, right? Because obviously it'd take us thousands of years just to get to Alpha Centauri, let alone, to a vantage point to see our own galaxy from a distance. So but the number of stars in our galaxy is about 100 billion. There are 100 billion stars in our galaxy. And our galaxy is one of hundreds of billions of galaxies, which is the current estimate of the number of galaxies in the whole universe. Maybe as many as 1 trillion. So that's a lot of stars, right? Yeah, which is a technical term. So, how much larger is the Virgo supercluster than the local group? I gave it away a minute ago, but who can tell me the answer? I need to get a list so I can call on people. But for now, I'll just take volunteers.
10 times bigger.
Thank you.
uh,
Were you going to say that too?
Yeah. I just couldn't figure out how to unmute.
Oh, yeah. Yep. Technical difficulties. Yep. 10 times bigger. Absolutely. That's powers of 10 for you. All right. And then we already did this one. How large are voids compared to the universe as a whole? All right. So, and they're 100 times smaller and a little bit more, because if we really wanted to consider the coefficients, we could take the 8 and figure out how many times does 1.5 go into 8. Well, we could say it goes in, let's see, so 3 times into 6. So, 4 times into 7.5. So if we rounded it to 4, well, then the difference then wouldn't be 100 times bigger, but 400 times bigger. So you could say the universe is 400 times the size of an average void. All right. So I mentioned the light year. Okay. So this is one of the key kind of like quantities that we're going to work with in this class. We're also going to work a lot with something called the astronomical unit, which is covered more in the early chapters, but the light year is more fundamental in a sense. So we're going to start with it. So the distance light travels in 1 year is what the light year represents. So a lot of people think that the light year is a measurement of time, which is totally fair because it's got the word year in it, but it's not. It's a measurement of distance. Okay. It'd be like if I, referred to like the donkey year, which is how far a donkey can walk in 1 year, right? Or the donkey day, which is how far a donkey could travel in 1 day. I was thinking of that because, like mule trains, and so maybe it'd be the mule day. Back in 19th century West, people travel by mule or, carry things that way. So, could be a measurement of distance, right? And actually people, that's, if you think of like history, think of like the Spanish missions in California, they were spaced one one walking day apart. So a walking day was how far a person, like a healthy adult, could walk in 1 day. So that was a way to measure distance based on, speed. So same thing with the light year. All right. But the great thing is that unlike those other measurements where they're a little inexact because people walk at different rates, right? Or mules or donkeys walk at different rates. Well, light doesn't travel at different rates. Light always travels at exactly the same speed. It's a fundamental principle of physics, been heavily tested, okay? And the reason that actually that Einstein even proposed, because it was Einstein who first proposed the concept that light had to always travel at the same speed, actually has to do with the very intuitive idea that physics itself can't vary at different locations. So in other words, the same physics that dictates, everything on Earth has to also apply to some other planet in another solar system or another star in another galaxy. So physics is not location dependent. And so, which seems like a natural assumption, right? Or at least a good starting point. Well, that's what led to the idea that light has to always travel at the same speed. You can never catch up to it. Even if you're moving at 99% the speed of light, if you were to measure light in that moving location, that moving reference frame, you would actually measure the same speed as someone that was at rest. Okay, so it's really kind of neat idea. But that the distance that light, with its great speed of 299,792,458 meters per second, okay, that's how fast it travels. If you take that and you multiply it by how many seconds are in a year, right? Because you just take, you got your seconds, you multiply, 60 seconds into a minute, you multiply 60 minutes into an hour, then you multiply 24 hours into a day, then you have to do a year. By the way, every time we talk about a year in astronomy, and this is super relevant because a light year is such a common unit, we assume that there's 356.25 days in a year. And that 25 is important. So there's not 356, there's 356.25. That's where you get, that's how you get the correct value. And that's actually why we have leap years. Okay? So take that speed, multiply it by the number of seconds in a year, and you get this number right here. 9.46 times 10 to the 15 meters. Remember how I said it was close to 10 trillion kilometers? Well, if I was to convert this to kilometers, I would divide by 1,000, which is dividing by 10 to the 3. Well, that would take the 15 in the power and make it a 12, because 12 minus 3, or 15 minus 3 is 12. So, well, then 9.46 is almost 10. So that's where you get the almost 10 trillion kilometers, which is relatively easy to remember. So if you can remember that a light year is about 10 trillion kilometers, you'll always be in a good place to make estimates. All right, so that's how we get all of these sizes over here. So we can convert directly from meters to light years with this conversion. Okay, so this would be a conversion formula, something we could use to convert. All right, so distance to Andromeda, 2 million light years, or 2 times 10 to the 22 meters. And now, what are we seeing in this picture? We're seeing a galaxy, because that's what Andromeda is. I told you that it would come up later, and maybe some of you knew and just didn't want to tell me when I asked, or weren't paying attention, which is fine. But, the Andromeda galaxy is our neighbor. It's the closest galaxy to the Milky Way. All right, so which of these correctly describes the distance to Andromeda?
Would it be number 3?
So 2 kilolight years?
Maybe.
Maybe, yeah. Yeah, so this question is kind of like just like testing what people already know, because these letters, right? They all represent different powers of 10, but you you don't necessarily know them, right? So
Correct.
yeah. So K, let's do this real fast. K is is 10 to the third. So it's 1,000. So that's a kilo. M is 10 to the 6. And that is called a mega. So it'd be mega light year. And it's a million. So then which is it? Is Andromeda 2,000 light years or 2 million light years away?
Million, right?
Yep. Yep. So it would be 4. 2 mega light years. And we will see that notation. And they're called the metric prefixes. Has anyone seen them before? These the different letters to represent powers of 10? Kilo, mega, giga, para, peta.
We briefly discussed them in chemistry.
Okay, cool. Thank you for sharing. Cool. All right. Yeah. And then, yeah. Yep. So, I'll always, like in any math problem, I will always provide a little like parenthetical note or something. I'll say what they mean. Okay. But I'll still use them. But they always make sure that I reference what they are. There's also lots of great tables. If I remember, I'll post one that just, is like an image that shows them all as a good reference.
Thank you, because I'm going to have an extremely hard time learning all this.
Yeah, it's a lot of upfront, but we're actually seeing a lot of the trickier ideas with those rules of multiplying, powers of 10, even just talking about scientific notation, this is most of the hard math in the whole class. Well, it's just sort of, I'm just giving you an upfront, not to scare anyone off, hopefully, but just so that we see it all, right away. It won't get any harder. Really, one of the only things we're not saying today is like anything with logarithms, but that, we can wait a week on that.
Yeah, plus you said the math is only in the homework, right?
Yeah, well, yeah, but it is 20 points, so it's 20% of the test as well. So it's about a
Thank you.
fifth, a fifth of the points on the test. Yeah. Yeah, that's why I said I shouldn't have said it's only the homework, but it says because it does show up on the test. Yeah. Yeah. I think I considered only putting in the homework, but I found that, is the I would always have the test questions. They're just like the homework questions, but the values are changed. And so it really rewards, just like, if you've done it, if you know the steps, then you can do it again you know, on the test.
Thank
And
you for that.
yeah, and generally people have been, when I did the whole semester class just finished at Solano, people did really well. They actually lost more points on the essays than on the math questions.
Oh gosh.
Yeah. But I think, yeah, I think that maybe just because they had the solutions to refer to, and so they could just follow the steps. But that's
Confident
that's
I'll
fine.
do well.
Yeah, exactly.
Just
If
want to say.
if they could do it, I can too, right? Oh yeah,
Yeah.
by the way, here is I was gonna show the size of a galaxy. So this is a representation of the Milky Way galaxy. It's obviously, like I said, you can't actually take a picture of it, but we've been able to map it out. So think of this as like a collection of data that's being represented by this figure. And so it's cool. It's like really detailed. I'll zoom in a bit. And so it shows like kind of the different arms of the galaxy. It even shows where we're located, which is on the Orion Spur, or it's called the Orion Arm. So that's actually the name of the arm of the spiral galaxy, because that's what these are called. They're called the arms, and the whole thing spins. It takes about 200 million years for it to make a full rotation. So it's made many rotations in the age of Earth, because Earth is over 4 billion years old. 200 million years takes you back to like early dinosaurs. They went extinct 60 million years ago. But the whole size of of the galaxy, that is, from edge to edge, is about 100,000 light years. Now, notice my habit of doing that. When I see scientific notation, I translate it into words if I can, right? So I look at this, I see 10 to the 5. I'm able to just read that as 100,000. That's not necessary, for you to do, but it just comes with practice, and, it's something you can certainly write out on paper and work out. But I'm just used to it. And so that's the whole size. That does mean that if light it was created on one edge of the galaxy, it would take 100,000 years to see that light on the other side. Okay, so that in other words, if like you on Earth right here in Orion's arm are looking towards the center of the galaxy, you're seeing light that was created 30,000 years ago, because it's traveled a distance of 30,000 light years, or 3 times 10 to the 4 light years. So every time we look at distant objects, we are looking back in time, which is neat because we get to see how things were. So it's like immediate cosmic archaeology in a sense, right? But it's also a limitation because we can never see what is currently happening, right? We are forced to look back in time. Okay, so that's the size of the Milky Way galaxy, 100,000 light years, or 10 to 21 meters. The distance to the center. And let's finally get down to distance between stars. This is going back to the grapefruit, right? So 4.4 light years. Notice it gave us a slightly different value before. And if that frustrates you, that's actually because the Alpha Centauri, the closest star to us, is a 3-star system. So it's 3 stars that orbit each other. So almost every time you look up the distance, you find a different value because it depends which one they're referring to of the three stars. So that's just a little thing to be aware of. It's not a big deal, but because we mostly just care about it for comparison's sake. All right, so I have a question for you. If we send a message to a Centauri, so that's someone that, lives, some alien, right, that lives out there in some Earth-like planet orbiting Alpha Centauri, how long must we wait before checking for a response? And use the 4.4 light years as the distance. So if I send a signal, like a radio signal, how long would I have to wait to get a response?
Is
Who
it
can give? Yep. Go ahead.
is it number 2?
No. Do you have another guess?
3?
Yeah, because they have to receive your signal and then send one back. So it's 4.4 years there, 4.4 years back. Yep. So the quickest response we could expect is 8.8 years. So if we sent a signal that said hello, we have to wait 8 years, and then they say, hello, who are you? Right? It'd be a very slow conversation, which is a major, major limitation, right? About being able to communicate, 'Cause there's no way around that. There's absolutely no way. In science fiction, they always, show people, you know, communicating across the galaxy, but you'd be totally isolated. There'd be, it'd take years and years to get signals back and forth, unless you had some way to, rip space and time, like they like to talk about wormholes or something. Okay, so that's the distance, 4.4 years. All right, is the travel time. The distance is light years. And I'll wrap up in the next couple minutes, and then 4.4 years back. I just want to get to a good stopping point. Solar system diameter. All right, so there we go. It's a tiny fraction of a light year. Notice that it's a thousandth. So if you were to read this decimal value for the size of the solar system, you could say it's 2 thousandths of a light year. So it's really measured in light minutes or light days, actually. And that takes us to the other unit, which I had mentioned a few minutes ago. Great thing to wrap up our class with, which is the astronomical unit. All right, so I know we've seen a lot today, but two big takeaways are going to be the light year. What is it? How long is it? Okay, expect that on tomorrow's quiz. And the astronomical unit. What is it? How long is it? Okay, so a common distance scale that's useful inside the solar system is this astronomical unit. The light year is useful to talk about distances between stars or within a galaxy or even between galaxies, okay? But it's not useful for talking about distances inside solar systems because solar systems are just too small. So, but the astronomical unit still looks like a big value, right? So at 10 to 11 there. But if you consider that to a light year, which had 10 to the 15, you can think, well, okay, that's 4 powers of 10 or 4 orders of magnitude, 10,000 times different. In other words, the astronomical unit is less than a 10,000th of a light year. And it's also directly related to Earth because it's the average distance between Earth and the sun. I say average because our orbit around the sun is an ellipse, not a circle. So sometimes we're closer to the sun, sometimes we're further away by a distance of about 4 million kilometers. But this value right here is equivalent to 149.6 million kilometers. Okay? So let me see if that's, yep. So if I'm going to write that out real fast. So there we go. So 1 AU is equal to 140. So this is, I'm not doing scientific notation. I'm just writing it as a phrase. So 149.6 million I'll hook up my tablet next time so I can write that way. And then km for kilometers. And that's really kind of the best way to quickly think about the distance. And you can round it to 150. So it's about 150 million kilometers, the average distance from Earth to the sun. So then we have, what is the solar system's diameter in AU? Well, you can convert over and we get a value. I won't ask you to do it right now. I would recommend getting a calculator or paper to do it. Don't try to do it in your head. But you get about 134. All right. Neptune, on the other hand, is 30 AU out. All right. Neptune is the most distant planet, by the way. So the most distant planet from the sun, there are 8 planets, because remember, Pluto is not a planet, it's a dwarf planet. And Neptune is the furthest at 30 AU. This is showing Neptune's orbit at 30 AU. It's the dashed line. Okay. And you can see in comparative size, Saturn's orbit, Jupiter's orbit. Well, first is Uranus's orbit, then Saturn, Jupiter, and then much smaller are all the little terrestrial planet orbits: Mars, Mercury, Venus, Earth. You can see they're very crowded in. And we'll talk about that trend in the solar system. Okay, so then how far is the Earth from the sun in AU? Well, I told you it's exactly 1. That's how we define it. Yeah. All right. So I'm sorry if I'm going fast. Just wanted to get to the end here. So there we go. And then scale. Oh yeah. So we can use the football field real fast to talk about the overall. So I did this with the grapefruit. Let me just show you. So there's Earth, Moon. Okay. All right. It was just going back to it. So quick follow up here is that, we talked about, the grapefruit size and all of that. Well, if you had the Earth and the Moon, they would be about 0.3 inches would be the distance between them, or 9 inches rather. Right. And then 0.3 inches, that was the ballpoint pen. Okay. I say that is a great stopping point. So we'll go ahead and wrap up 4 minutes early, unless we have any questions. So prepare your questions, but I'm going to stop the recording in the meantime. So let's see. Any last questions before we wrap up? I see there's stuff in the chat. I'll refer to that. I had it hidden while the slide was going. So otherwise it would have shown up. Let's see. Cool. Oh yeah, so someone was talking about the different mesh stuff. Nice. All right. Cool. Yeah, I don't have a good way of having the chat up and not having it show up on the video for the recordings. So that's why I wasn't seeing it. So I'll try to see if I can. There may be a way around that, because I would like to be able to see, if you want to write me something rather than just turn on your audio. Because especially I missed some good comments that I would have liked to see. Oh well. All right. So we're really good. Nothing's on your mind. Send me a message. I got 10 unread ones, but I know some of those are people that I just missed today. I got some people to add, but I'll respond, as quickly as I can to anything that you have. If you do remember a question.
Can you direct us on where we should study before tomorrow's class? Is it just in the chapter 1 and chapter 2 sessions of the book?
So yeah, for the quiz tomorrow, just chapter 1.
Okay, chapter 1.
I gave you a couple of hints. Make sure that you're good on the light year and the astronomical unit. When we do the quiz, I'd recommend having that ready and open to look at. But besides that, the biggest thing is to read the chapter. You can skim certain parts, but just look over the sections, whether in the ebook or the PDF.
Thank you.
Yeah, absolutely.